Hi there. Hello there again. I don't know what that was, but it was a nice distraction. I want to use this video to introduce you to classification with support vector machines. And so this lecture deals with the support vector machines, and we want to understand what they are and how to use them. So reminder again, classification is a supervised learning technique, and meaning there's a y variable or something you're trying to predict. You're trying to predict whether the customer will default on the credit card offer or not. You're trying to predict whether the customer will buy from the LL catalog if you mail it to them or not. So classification, the y variable is typically a 0 or 1. And there are many paths to performing classification, as we have seen so far. You could do k nearest neighbors. You could do decision trees. You could do logistic regression. And in this video, I'll introduce you to something called linear discriminant functions and support vector machines. So this is a good opportunity to kind of take a step back and understand the intuition behind all of these techniques, so that you see all of them together in a single place. So I want to remind you what the classification context is. We are given a feature vector for each customer. So each customer in your database is described by some n different variables, x1, x2. So if you had two variables, age and income, x1 could be age, x2 could be income. But typically today you have lots more information available, about the customer. For instance, their home value, the zip code they live in, There could be lots of interesting things you could use for classification. So we're also given a training set, meaning a small data set where maybe it may not be a small data set today with the availability of big data sets, but for the training set we also know the value for the different variable. For instance, we know whether this particular customer with this feature vector responded and bought from the LL Bean catalog or did not buy. And so we use the training set with the knowledge of the Y's to fit whatever model we are fitting, right? And what is the purpose of using the training set to fit a model? The real value of the model comes about when you want to kind of let the model loose on a future data set, and we may call that a test data set or a future campaigns, marketing campaigns. Remember, data science and data analytic thinking is useful when you have really no choice. If you have to send or evaluate offers to 1 million different credit card customers, you don't want to sit down with an envelope and be calculating some stuff about each customer. It'll take you a very long time if you did that. That's the reason this material is, or this class is valuable, or data science is valuable, because you can automate decision making using all these models, and you can let the computer pick the customers to whom you want to send the offer. So that is the machine learning process. Use the training set to fit the model, and unleash the model on future test data sets or future customers to predict what they'll do. So here's a quick survey. I want to remind you of the k nearest neighbors. K nearest neighbors kind of, this is just plotting the k nearest neighbors for two variables, or for a feature vector with just the income and age, but in real life you could have more than two features. But the intuitive idea is this black square is a new customer for whom you're trying to predict what their class label is. The yellow circles are good credit risks and the red triangles are bad credit risks. And you kind of measure the for k equal to 3 or k equal to some number, you measure the distance of the new customer to the 3 closest neighbors, and then you kind of put it to a vote. So this new customer, for instance, is closer to 2 bad customers and 1 good customer, so that this customer may be called a bad customer by the k nearest neighbors algorithm. Okay, that's what we did with k nearest neighbors. Let's go to decision trees. Decision trees, we formulated a set of rules which basically broke the customers, all the customers in the world, into mutually exclusive and collectively exhaustive segments. So here's a classification. We first divide the customers based on balance bigger than or less than 50,000. For customers with balance less than 50,000, we split them again into, customers with age bigger than 50 or less than 50. And for customers with balance more than 50,000, we again split them into customers with age bigger than 45 or less than 45. And that kind of sort of led to a classification, because you can see that customers with age less than 50 and balance less than 50, they kind of tend to be black dots. And customers with balance more than 50 and age more than 45, they tend to be the crosses. So, whatever they are, this is one type of classification, this is another type of classification. And here is a pictorial view of the same decision tree. All the decision tree is it's a set of rules. And if you go from the root of the tree all the way to the leaf node predicts a classification for this particular type of customer. So for customers with balance less than 50 and age less than 50, the leaf node predicted write-offs. That's how decision trees worked. Then we looked at logistic regression, and again, the process is the same. Describe the customer with a set of features, x1 through xn. You know whether the y variable for the training set. And all logistic regression did was it built this logistic function, which is actually a probability. And logistic regression is an example of a parameter fitting algorithm, meaning it is searching for the parameters beta naught, beta 1, beta sub n, such that the predicted probability pretty much reflects what you see in the training's data set. Okay. So again, logistic regression was the first of what we call the parameter fitting algorithms, in the sense we are looking for parameters that give you the best explanation for the data. And this is what the logistic regression, this is what the probability function looks like for logistic regression. Okay, let's finally cut to the chase. And we are going to look at linear discriminant functions. And again, this is a parameter fitting function, in the sense if you're given a feature vector for a customer x1, x2, x sub n, you're going to basically weight feature 1 with weight w1, feature 2 with weight w2, feature n with weight wn, and form a composite function, kind of like w1 multiplied by x1 plus w2 multiplied by x2 plus w sub n multiplied by x sub n. And your classification rule could be, if this composite function is, let's say, bigger than 0, you may choose some other cutoff, but let's say it's bigger than 0, you classify the customer as y equal to 1. Otherwise, you classify the customer as y equal to 0. So linear discriminant functions also are similar to logistic regression, in the sense it's a parameter fitting algorithm, in the sense you got to be smart and figure out what the best values for w1, w2, w sub n are, so that on the training data set, this function is able to classify the y equal to 1 compared to y equal to 0. That's the basic idea. So linear discriminant functions are intuitively very easy to understand also. And here are some pictures. Let's again look at a bunch of customers described by two features, balance and age. And let's say the customers fall into two classes, the crosses and the dots. And you want a linear discriminant function to kind of separate them, right? You want a way to figure out, whether when a new customer comes along and you know the balance and age for the new customer, you want a rule to figure out whether the new customer is going to be a cross or a dot, right? And what you can do, or what the linear discriminant function does, is it tries to pass a line between the crosses and the dots. And you would say, if the new customer falls on one side of the line, you would call them a cross. If the new customer falls on the other side of the line, you would call them a dot. And as you can see, this is not an easy process, because there are many possible lines that separate, in this picture, that separate the crosses from the dots. I have to unfortunately confess that in real life, the crosses and dots are not as neatly separated like so. In real life, what tends to happen is, they may be separated for the most part, but right here in the middle of the crosses, you will see a dot, and in the middle of the dots here, you'll see a cross. and then it becomes or sometimes impossible to run a function through that separates the two of them. But let's assume for now that you can separate them with a line. And even if you can separate them with a line, you can see there are many possible line solutions that does the separation effectively. And so we come to this idea of something called a support vector machine. And a support vector machine chooses something called a maximum margin classifier. So here is the support vector machine, and this is the linear discriminant function the support vector machine is recommending. And the support vector machine tries to find something called a maximum margin classifier. Intuitively, it's trying to kind of fit the fattest cylinder between the crosses and the dots and make the cylinder as fat as possible, so that you have a robust way to separate the crosses from the dots. Okay, so that's essentially what a support vector machine is, and of course in scikit-learn you have packages that will fit a support vector machine for you. That's what we're going to see next. And but to summarize, support vector machines are linear discriminant functions, and they are also belong, like logistic regression, they belong to the class of parameter fitting algorithms, in the sense you got to choose the weights for the linear discriminant function, for the weights for the features that performs the classification most effectively. Okay, one final word. You may be thinking, man, or do I really need so many different classification techniques? How do I choose a technique, from the plethora of techniques that seem to be available? So I want you to be very aware of the business context when you choose a tool for classification. And how to choose, if you could apply all these techniques, logistic regression, support vector machines, decision trees, one reasonable answer is simply do the training test data set, try multiple techniques on the training set, and see which technique works the best on the test set. That's the technique you choose for that context. And different contexts, different techniques work well. Logistic regression may work well for database marketing. Sometimes you may choose a decision tree not because it's excellent at classification. It's pretty good at classification, but decision trees are very easy to interpret and explain to senior management, and so the choice of the technique depends upon a combination of how effective is the technique for the business problem, and also how easy is it for you to communicate the technique to other people in your company. So this was, again, to summarize, an introduction to support vector machines, which is another classification technique. And support vector machines are parameter fitting, belongs to the class of parameter fitting techniques, and uses linear discriminant functions. Okay, see you in the next lecture.